So throughout the unit, we're going to connect the idea of a limit to the slope of a tangent because, as we discussed yesterday, the slope of a secant is the rate of change between 2 points. But what calculus is really interested in is the instantaneous rate of change or the slope of a line that touches a curve at 1 point, and that's called a tangent. The problem is we can't calculate a slope with 1 point only. We need 2 points. So we start to look at, well, what happens if we have secants and that second point moves progressively closer and closer and closer to the point we're interested in. The closer they get, the more it resembles the slope of the tangent. And whenever we approach something in math, we talk about that being a limit. So this is going to be the fundamental definition for the limit of a tangent. H represents the distance between the 2 points. These are the y values for the 2 points. The horizontal distance is h. So as the distance between the 2 points goes to 0, this will find us the slope of the tangent. You don't have to worry too much about this now, but this is where we're heading to. But in order to work with this limit definition, we need to know how to work with limits just in general. So there are strategies that we use when finding limits. So the first one is substitution. If you can put a number in and there's not a problem with it, you just do that. A lot of times this is missed because most often we're looking for limits of things that can't just be substituted. But if it works, that's where you start. If it doesn't work, and I'll show you what I mean with some examples, then that's when we start with these 3 strategies. We'll add some more if you're in calculus next semester, but this is kind of where we start. Factoring, rationalizing, and finding a common denominator. I'm going to work through a couple and hit all of those. So let's look at the first one. We want to find the limit as x approaches -1 of x squared minus 4 over x plus 3. There's no problem with me subbing -1 into there. Usually the problem comes from the bottom equaling 0, but -1 plus 3 does not equal 0. So this can be a straight substitution. The limit is going to equal -1 squared minus 4 all over -1 plus 3. So that's going to give me -3 over 2. I just calculate the top and calculate the bottom. Most often than not, though, it's not just a straight substitution question. If we look at number 2, we're looking for the limit as x approaches 1 of x squared minus 6x plus 5 all over x squared minus 3x plus 2. If you try and put positive 1 into this bottom, you will get 0. And that's what I mean by it not working. We can't sub 1 into this and get a defined answer. But as the function gets closer to 1, something's happening, and we want to figure out what that is. So I hope you recognize these as trinomials, and we're going to proceed just by factoring them. Just finding a marker that works. The nice thing is that they are normal trinomials, so I can go bracket, 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 bracket. When you're calculating a limit, it is really important that you carry the limit notation until you get to a point where you can sub the number in. So this is the limit as x approaches 1, x minus 3, sorry, I can't do this, sorry, x minus 5, x minus 1, x minus 2, x minus 1. Just be careful with the signs. Now I can cancel the x minus 1's, but I have to be careful because 1 is what make the 0, and when you're canceling, you're actually doing the division. So when I say that, I actually have to say I can do that as long as x doesn't equal to 1. But now we've created something that I can sub 1 into. So we make a rule and then we break it right away. This only works if x isn't 1, but now I've created something that I can sub 1 in, and I get -4 over -1 or just +4. Because I can do now 1 minus 5 on top, 1 minus 2 on the bottom, because I don't have any issues with 0 being on the bottom. So the function itself is not defined at 1. There would be a hole. It would be discontinuous. But it is approaching 4 as it gets closer to 1, because that's what a limit is. What is the graph approaching? Not necessarily what it equals. Example 3. The limit as x approaches 0 of the root of 4 plus x minus 2 all over x. I definitely can't put x equal to 0 in here because that would give me 0 on the bottom. So this is strategy number 3, which is rationalizing. I want to get rid of the root and see if that helps me. We rationalize by multiplying by a funky 1. The funky 1 is always made up of the conjugate of the part with the radical or the root. So the conjugate of the root of 4 plus x minus 2 is the root of 4 plus x plus 2. So I keep these two quantities the same, but I change the operation in the middle. I don't want to change the value of this, so my only option is to multiply by 1, so I have to put the exact same thing on the bottom. So now I get the limit as x approaches 0. On the bottom, I'm just going to put x with this funky conjugate in a bracket. But now the top, I've created a difference of squares. So when I FOIL these out, the root of 4 plus x times the root of 4 plus x just gives me 4 plus x. The root of 4 plus x times positive 2 is 2 root 4 plus x. But then I multiply it by negative 2, and I have negative 2 root 4 plus x. They cancel out. Then when I multiply the last two, I get minus 4. So by picking the conjugate, you'll always get on either top and bottom that root to go away. I don't really care that I have it left on the bottom. It's not a problem for me to put 0 into this part. I'm going to clean up the top a little bit. So I just get x over x root 4 plus x plus 2 because the 4 and the negative 4 cancel each other out. Now I can cross off x as long as x isn't 0 because that's what would make the chunk that I crossed off equal to 0. So I'm left with the limit as x approaches 0 of 1 over root 4 plus x plus 2. The bottom isn't pretty, but there's really no problem in me subbing 0 into there. 1 over root 4 plus 0 plus 2, which is going to give me 1 over 4 when I finish it, because the root of 4 is 2, and then I have 2 plus 2 on the bottom. 4. The limit as x approaches 2 of x squared minus 4 over 1 over x minus 1 over 2. If I put 2 there, I get 0 on the bottom, so I can't just substitute. I'm going to rewrite this so I don't have fractions over fractions. But because I'm dividing by the 1 over x and the 1 over 2, I have to put it in brackets. Now I'm going to find a common denominator in this bottom. And my common denominator is going to be 2x. I just take them and multiply them together. So this gives me the limit as x approaches 2, x squared minus 4 divided by 2 minus x over 2x. This one I had to multiply by 2 and 2. This one I had to multiply by x and x. So now I'm going to flip and multiply. I'm also going to leave some space here because I'm going to talk about that in a second. But because I've created one fraction, now I can change the division into a multiplication and multiply by the reciprocal. I couldn't do that up here because I had two fractions. This now is one fraction, so I can flip it. I'm going to I'm going to factor this difference of squares while I'm here to x minus 2 and x plus 2. Because here's the problem. I can put 2 in here. It doesn't matter that I get 0 on top. This is the problem. X minus 2 and 2 minus x are exact opposites of each other. So they cancel, but instead of canceling to positive 1, they cancel to negative 1. And I can only do that as long as x is not 2. This is a necessary part when you do the canceling. But now I'm left with the limit as x approaches 2, negative 1 times x plus 2 times 2x. I can sub in now. So that's going to be negative 1 times 2 plus 2 times 2 times 2. You don't have to show a lot of work, but it's going to be negative 16 because I get 4 in the first bracket and 4 in the second bracket. I'm showing all the substitution steps so you can see what I've done, but you can kind of condense this down and get to your answer quickly. You can only drop the limit, though, when you sub in. Number 5. The limit as x approaches 3 of x squared minus 6, x minus 6 squared minus 9 all over x minus 3. You could FOIL this out and collect like terms, but if you recognize the top as being a difference of squares, because I have chunk squared minus 9, so I'm going to have chunk plus 3, chunk minus 3, so x minus 6 and x minus 6. So when I clean up the brackets, My first bracket gives me x minus 3. My second bracket gives me x minus 9. I had the x minus 3 on the bottom. Now I can cancel out the problem because that's what gave me 0. I can only do that if x isn't 3. But now I've created something that I can see what would it be if x could be 3, and it would be 3 minus 9, which would be negative 6. Now the only other thing I want to talk to you about is a piecewise function. A piecewise function is something that's made up of pieces, so it's not the same thing all the way along. So in this case, f of x is equal to x squared for x greater than or equal to 0, or it's equal to 2x minus 1, for x less than or equal to 0, 2x minus 1 for x greater than 0. If we were to graph this, I have a parabola for x less than 0 and equal to 0, and then for, whoops, oh my goodness, tell it's been a couple weeks off. There we go. I have a parabola for x less than or equal to 0, and then this line, my y-intercept would be at negative 1, but I put an open hole there because this only starts bigger than 0. 0 isn't technically included. And then the slope is 2 over 1. So I would go up 2 over 1, and I'd have a line that looked like that. So that's what would be considered a piecewise function. It's a function because it passes the vertical line test, but hopefully from the last unit you recognize this would be a discontinuous function because I'd have to lift my pencil in order to draw it. So now, we're going to look at the limit as x approaches 0 from the right, f of x. Well, from the right is bigger than 0. So we can see it from our graph that as I get closer to 0 from the right, I'm approaching negative 1. Or you can say, well, wait a minute, the right is bigger than 0. So that's 0 to the right, and I just go 2 times 0 minus 1 gives me negative 1. Now I'm going to do the limit as x approaches 0 from the left. So that's on this side, or smaller than 0. So I can do it from here and say, okay, as I'm approaching, I'm heading towards 0. Or you could say left is less than 0, so I would sub it into here. 0 squared is 0. So I can calculate the right-hand limit and the left-hand limit. What happens as I approach from the right? What happens as I approach from the left? But now if we want to talk about the overall limit at 0, so the limit just as x approaches 0 from both sides. Now, for a limit to exist, you have to converge to the same answer from both sides. I can see if I follow the function along here, my fingers are going to miss each other. So I'm not converging. So when these limits are not the same, the overall limit does not exist, and we represent that with D and E. In order for the limit to exist, it has to approach the same number from both sides. Even if there's a hole there, if you had a function that looked like that, that limit would still be 2 because my fingers approach each other. The limit from the left-hand side and the right-hand side are the same. Now if I look at the limit as x approaches 2f of x, well, 2 is going to be somewhere over here. I am going to approach the same number. It's not around this kind of area of discontinuity. 2 is bigger than 0, so I can literally just go in here and I can see that the answer would be 3. The only problem on this graph is going to be the point 0 because that's where the point of discontinuity is, or my graph is at 2 different places as I get closer to 0. So I gave the handout out yesterday. I'm also going to post a picture of it in with this video so that you can work on those. The answers are there, and we will take a look at some questions like that on Thursday. I can go over homework questions. I want you to do all of them, and the numbers that I've written in pencil that photocopied with it are the answers that I got, so you could check your work.